Okay, in the next example, we consider a collision of two objects. Okay, two objects that interact with one another. When two things collide, they exert equal and opposite forces on one another. So we are given a situation, and we're given a little bit of information where we can find F net delta T very directly. I think we're given F net and delta T. And it might be something like 400 newtons for 3 milliseconds or something like that. Whatever the actual given information is, it's very straightforward to calculate the impulse, 1.2 newton seconds. And that's going to be the magnitude of the impulse. Okay? Now, we have two objects interacting, and each object exerts a force on the other so that the two forces are equal and opposite, which is why I've got absolute value signs around this. For both objects, the magnitude of the impulse is 1.2 newton seconds. But for one object, the impulse is going to be in the direction opposite the impulse for the other. Okay, the impulse experienced by one object will be equal and opposite to the impulse experienced by the other, because of course in a collision or in this type of interaction we have equal and opposite forces acting for equal and opposite time interval. Okay, so now we can just state that, okay, F1 delta T is equal to negative F2 delta T. Okay, now one of these forces is greater than zero, the other force is going to be less than zero, and it depends on how we choose our directions, what's positive and what's negative. But let's just suppose that F1 is greater than zero. Without any loss of generality, we can make that assumption. So now let F1 be the force acting on the 100-gram mass. There are two masses, one mass being 100 grams and the other mass being, I believe, 200 grams. Okay, so F1 is positive. We assume a positive force. The positive force, the positive direction, is that of the force acting on the 100-gram mass. So now we know that F1 delta T is 100 grams times delta V1, where delta V1 is the change in velocity of the first mass, the 100-gram mass, so that the change in velocity of that mass is 1.2 newtons per second, newton seconds, divided by 0.1 kilograms. Remember that a newton second simplifies to a kilogram, or breaks down to kilogram meter per second, so that the kilograms will divide out just like they did up here, and we end up with a change in velocity of 12 meters per second. Okay, the other mass, well, we can say that negative F2 delta T is going to be this second mass times the change in velocity of that mass, so that the change in velocity of that mass is going to be negative 6 meters per second. Because, and I didn't write out the details, but M2 is 200 grams. So that we're going to be dividing 200 grams into a negative 1.2 newton second impulse, and we're going to get negative 6 meters per second. So whatever happens, the less massive object is going to change its velocity by 12 meters per second. Let's say this is the first object, and it's coming toward the second object. Okay, and whatever the velocity of these things are, this thing's going to go off, and the velocity change from this to this is going to be plus 12 meters per second. And this is going to lose 6 meters per second. Now, there are many ways that collision could go down, many ways that could occur. And we're not going to say too much about all the specific ways in which it can occur, but in this case, the initial velocity of the first mass was said to be 4 meters per second. The initial velocity of the second was negative 3 meters per second. Okay? If V1 prime stands for the velocity of the first object after collision, that means it was moving at 4 meters per second, and it changed velocity by 12 meters per second, so it ends up at 16 meters per second. Okay. The second velocity after collision, well, its velocity before collision was negative 3 meters per second. Then velocity changed by negative 6 meters per second, so now it's moving at negative 9 meters per second. Now, this isn't a completely realistic collision because of a couple of things. One is, unless there's some sort of potential energy changing here, like maybe an explosion, chemical potential energy, or a spring-loaded, the kinetic energy of these two objects, total kinetic energy after the collision, would be greater than before the collision, so we'd be violating energy conservation. Okay? So that's not possible. Also, the second object is moving in the negative direction. Let's say this is a negative direction. The first object in the positive direction before the collision. And after the collision, the first object is moving even faster in the positive direction, and the second even faster in the negative direction. Among other things, that might invoke an image of the first object passing through the second. Now, it's possible that the interaction between these is not a physical contact interaction. For example, you could have a cylinder with a hole in it, and that would be the first object, and the second object would be something that would pass through that hole. And in the interaction might not be one of contact. There might be some sort of electromagnetic interaction that causes this object to be sped up and this object to be sped up as the one object passes through the other. Okay, that's a little bit of a far-reaching or far-fetched explanation, because you would have to have, it's not all that far-fetched, you could create a mechanism where you would have that sort of electromagnetic interaction, so that as the one object passes through the other, it gets pushed harder in this direction, and this one reacts by speeding up in this direction. So it's entirely possible. Okay, well, we'll continue with the next example.